This is a really complicated figure, but it summarizes the internal structure of a typical neuron and its connections with other neurons. So, in a neural network, there are many such neurons, and all these neurons are actually organized into layers. So for a deep neural network, there can be quite a few layers, and each layer can potentially have many neurons, this kind of neurons. So here we are looking at one neuron that is located at layer L. So the layer index usually appears inside of parentheses. It appears inside parentheses, and usually as a subscript, as a superscript, So if you see a parenthesis and in a superscript, then the number inside of it is usually the layer index. The subscript J here, indicates that this neuron is the jth neuron inside of the L's layer. So its left neighbor will have a subscript J subtract 1, and its right neighbor will have a subscript J plus 1. If this layer has more than one neurons, right? If it has multiple neurons, then the left neighbor of this particular neuron is going to have a subscript that's J subtract 1, and then its right neighbor is going to have a subscript that's J plus 1, and both of its neighbors are going to have a superscript that's parenthesis L, right? Because they are in the same layer. The neurons at the same level have no connections whatsoever with each other. So all the neurons at the same level are not connected in any way. They are separate. So there are no connections among the neurons at the same level. No connections. A neuron can only connect with neurons that's immediately below its own layer, or immediately above its own layer. So for this neuron that's at level L, right? Its inputs can only come from the layer that's below it, L subtract 1, and its output can only go into the layer that's immediately above it, that's level L plus 1. Right? So it cannot have any kind of connections with the layer that's like a L plus 2 or L plus 3, that kind of thing. It cannot have connections with layers that's L subtract 2, L subtract 3, right? It can only have connections with layer L subtract 1 or L plus 1, right? That's the kind of a typical configuration of a typical neural network, right? The inputs to this neuron come from the layer immediately below it, right? So all the inputs are going to have a superscript that's L subtract 1, right? But you must notice that those inputs must be weighted by a certain weight, right? So the subscript I here denotes the neuron index inside of a layer L subtract 1, right? Here I'm using a different index, right? So J is the neuron index in layer L, right? For all the neurons that's inside of layer L subtract 1, I'm using the index I here, right? So each input is multiplied. Each input to this neuron from layer L subtract 1 is multiplied with a weight. The value of the weight is going to depend upon indexes of the layers they are connecting, the connections are connecting, and the indexes of the neurons they are connecting. So those weights are actually associated with the connections. And each of the connection depends upon the layer, right? And then the neuron that's in the lower layer, and then the neuron index that's in the upper layer, right? So WIJL here means that it is the weight for the connection that's coming out of the ith neuron in the L subtract 1th layer and comes into the jth neuron in the L's layer. So that's what these three indexes actually mean. You require these three indexes in order to actually uniquely determine the connection, right? So the connection is for layer is between layer L subtract 1 and L. So here you are using L here, right? And then it's connecting the ith neuron in the L subtract 1th layer, and then the jth neuron in the L's layer. So that's what this weight actually means. The weight is associated with the connection, and for each of the connection you need three indexes in order to actually uniquely determine it. So the second subscript here, for all the weights, for all the connections that's coming into this neuron, is always J, because this neuron's index in the L's layer is J. So its second index is always J, right? Because this neuron is the Jth neuron in the L's layer. Right? But the first subscript I should range from the first neuron. In the I subtract 1th layer to the last neuron in the L subtract 1th layer. Right? That's the range of the index, the first subscript I. It may go from like 0 to 10 if you L subtract 1th layer has like 11 neurons or something, or go from like 1 to 100 if the L subtract 1th layer have like 100 neurons. So I must have a range, right? So here it's WIJL, right? This connection is with the input that's Y I L subtract 1, right? And then this connection is with the input Y I subtract 1 L subtract 1, right? And this connection is with Y I plus 1 L subtract 1, right? So the input for this particular connection, the input for these three connections. Of course, you could have many connections, right? It doesn't have to be limited by these three. I'm just drawing the three arrows, but you could have many connections that's coming into this particular neuron from layer L subtract 1. The logit of this neuron is just the weighted summation. The weighted summation of all the inputs coming into this neuron. This calculation is actually linear with respect to the input, right? It's a linear function. It's a linear function. The logit is a linear function of the input. It's just a multiplication with a weight and then do a summation. This calculation can also be expressed as an inner product, if you actually know what an inner product actually is, right? So if you studied linear algebra before, this can be expressed as a as an inner product. Right? This summation, this multiplication with weights and then the summation can be expressed as a inner product. And then this logit, this ZJL, the logit, is then used as the input to a nonlinear function inside of this neuron. It must be a nonlinear function, and there are theoretical reasons for why, right? It has to be a nonlinear function. If it's a linear function, then there's no point of doing multiple layers of neurons. All the calculations can be just expressed with just one huge matrix vector multiplication. So you must have a nonlinear function inside of a neuron, and there are multiple choices for this particular nonlinear function. The most popular choices for this nonlinear function are the so-called ReLU function, the hyperbolic tangent function, and the sigmoid function. And each one of them have different variations. And each choice has its own advantages and disadvantages. The ReLU function is most popular in image processing, and it has a few variations of its own that address some of its shortcomings. We will spend some time to talk about different types of those nonlinear functions in a different video. Right? You can choose among a collection of those kind of nonlinear functions, right? And we'll talk about the trade-offs. The output of this nonlinear function, if you have picked a one nonlinear function, right, and then you can use the logit as its input to that nonlinear function, and that nonlinear function is going to give out one output, right? The output of this nonlinear function is denoted as yjl here, right? So it also has a subscript of j and then the layer index l, right? And then this output is then used as one piece of input to the neurons in the upper L+1 layer. So all the weights for the connections that's going out of this neuron are gonna have a superscript L+1. And then the first subscripts are all J, because all those connections are actually going out of the J's neuron in the L's layer. So that's because the first subscript is always J for all the weights. The second subscript for all the weights is going to depend upon the index of the neuron that this connection is going into in the upper L+1 layer. So here we are using a different index k here, right? If this connection goes into the neuron with the layer index L+1 and a subscript index k, right? Then this connection that's right next to it, right to the left of it, is going to have a second subscript k subtract 1, because it's going into the neuron k subtract 1 in the L+1 layer. And then this connection is going to have a second subscript k+1, because this connection is going into the neuron k+1 in the layer L+1.